Uh, Today we'll prove the intermediate value theorem. Right, so just as a remark, if f goes from Rn to Rm, then and K is compact, so continuous K is compact, then we have the following. So yeah, so if n is 1, okay, for general m and n, we have the extreme value principle. I.e. f of k is compact. Yeah, if m is 1, we have the extreme extreme value theorem. Meaning you have that it attains the endpoints and if you have both n1 and m1, you have the intermediate value theorem. Okay, so what is that? Let a less than b and continuous function on that interval. Then you have two things. If y is, let's take f of a to be less than f of b without loss of generality. Then you attain that intermediate value for at least one point. So the picture is, this is the function. And there's the y, and then you draw the line, and there's at least one guy that gets mapped to f of y. And the second one is the image of that interval. So this implies, right, so m, where this is the min, and this is the max. All right. So the progression is, where is it? Yeah. So for general dimension, you might not attain how do you say this? So f of k being compact means it contains its boundary. So that's the general statement. Yeah, so that's the general statement. Then if you map to 1D, you even have a nice ordering. And furthermore, if you map from R to R, you map intervals to intervals. So it becomes more and more regular. All right. Is that okay? Let me see. All right, let's prove this. By shifting, so let me say it this way. Without loss of generality, y is 0, and y is 0 by shifting to a different function, f of x minus y. So what we want to do, we want to find C in AV such that f of C is 0. All right. So for some intuition, yeah, so this is f of A, this is f of B, and we say that there is at least there's at least 1.10. All right. So one way to catch that zero is to consider the set f of x being strictly less than 0. So in the picture, so it will be all these points. So and then and let C be the supremum of V. So in the picture, this is C. Okay. Yeah, you don't have to wait in the lobby. Right. The claim is f of C is 0. All right. So we break the proof. We do it by way of contradiction. I.e., there exists some epsilon naught So there exists some epsilon naught such that f of c is bigger than epsilon naught. Okay, so then first case, we will disprove that f of c is bigger than epsilon naught. And then second case, right? Second case, I call it delta naught. Okay, fine. F of c is strictly less than minus delta naught. So we start with the first case. Okay, fine. By the epsilon definition, of sup of E, for every epsilon n, 1 over n, there exists xn in E such that you have the approximation by epsilon n. Okay. Right. Okay. All right. Now, two things. First, AB is closed. And so, how do you say this? Even though it might not be obvious at first, this makes it obvious. And so, since xn goes to C and xn is in E, which is a subset of AB, we get the non-surprising statement that C is also in AB, because a priori it's not obvious that C is in AB. So here we use that AB is closed. For counterexample, C, if you let C to be 0, 1, and, you know, let me see, 1/2 open, 1/2, you know, and take f of x to be x, and take y to be a half. So we need AB to be closed. All right. Second, by sequential continuity, is that okay so far? Let me see. Sequential continuity of f. What do we get? Xn going to C implies f of xn and also 1. Implies f of xn goes to f of C, which from 1 belongs to f of AB. Okay. All right. Almost there. So we have to break, we have to use 1 and 2 to contradict f of c is bigger than delta naught. Let's see, how can we do this? All right, so let's see. We have 0, delta naught, f of c. Right. Now, how do you say this? Approximate f of c by an error of delta naught over 2. Right, so for all n bigger than n delta naught over 2, then use here that xn is in E, and so f of xn is strictly less than 0. All right, so then you get the contradiction 1 is less than a half. So that's the first case, okay? Good. Now we contradict f of c is strictly less than minus delta naught. Now that's a nice argument. So since f of b is strictly positive, and that's because otherwise just let c to be b, we have c, and also, okay, one second. So we have this, and we prove that c is in AB. So we have c is strictly less than b. All right, so back to the picture. This is C, and this is B. Let me magnify it. All right, so C is strictly less than B. That means we can find points yn in here. So there exists yn in what do you call it, in C open B, you know, such that yn goes to C as n goes to infinity. For example, from homework 1, take yn to be rationals in, you know, c, y, c plus 1 over 10 to the n. Is that okay? All right. Fine. Good. So now let's see the contradiction. We start from the left now. By sequential continuity, again, we have f of yn minus delta naught over 2. So here is for all n bigger than n delta naught over 2. Then we have, so since yn is bigger than c, we have that yn is not in E, so we get that f of yn is strictly positive. So again, we get the contradiction -1 is bigger than -1/2, which is a contradiction. And that's it. Okay, any comments? Right, so what's the example? Right, let's do that example. Take the function minus, define -2 as x cubed minus x. So this guy is negative. But what is it? What do I want to say? Yeah, so it has, what do I want to say? Yeah, when you get close, it hits 0, then it goes like this, then it goes like, let me draw it bigger. So, and set y to be 0, then the solution to f of c equal 0 is -1, 0, and 1. So IVT gives you at least 1. Okay. All right. Yeah, of course. If you go on the syllabus, we say that. We mentioned this in the syllabus. All right. So that's it. Now we're going to move to uniform continuity. So let's start with an example to make sense of uniform continuity. So, okay. Let f of x be 1 over x. for x in open 0, 1. Okay. So it goes like this. All right. Now let's look at two different points. X1 being, what is it? Yeah, we can make it closed, it's fine. Let me make it bigger, it's fine. So take x1 to be 1 and take x2 to be 0.1. We want to study continuity. Of f at x1, x2. So suppose you say you set epsilon to be 0, 1. We want to find r positive so that, you know, x minus x1 less than r implies f of x minus f of x1 is less than 0.1. So you want this level of precision. All right. So let's see. For both of them, xi. You want to see. So let me just write. It's confusing. Let me do it for x1 first. All right. Where are we? Yes. So we reverse engineer. We have 1 over x minus 1 over x1 less than 0.1. 1 over x1 is 1. So we have 1 minus 1 over 10. 1 over 10. Okay. So what is it saying? It says that, you know, the lower guy is 1 plus 1, and the upper guy is 9.9. Okay, so the radius of this is a bit confusing. Is of that form, but I have the value. So apparently this is like, what do I say, 1 over 11, close to x naught. Actually, let me draw this bigger. So what are we saying? We're saying so 1 over x, 1 gets mapped to 1, and we want 0.1 accuracy. And so to do that, we have to come close within 1 over 11. Is that okay? So oh, I meant to write, what do I mean to write? Right, thank you. I meant to write 0.9. Okay. So let's see, right. But for x2, the same R doesn't work. What do we mean by that? So let's see. So this is a bit, let's see. So again, let me write what the statement is. For x2 equal to 0.1, we want to find R positive so that x minus x2 less than R implies f of x minus f of x2 is less than epsilon, which we put it to be 0.1. Okay. Right. So again, this is 1 over x minus 1 over x2. And let's see. So you have minus 1 over 10, 1 over x, and 0.1, and 1 over 10. So we reverse engineer. Okay, this is 10. So you get 10 minus 1 over 10. And 10 plus 1 over 10. Okay. So x would be in this interval. But so R for x2 would be equal to this, which is much smaller than 1 over 11. In fact, it's equal to what do we say here? 1 over 1,000. Okay, so again, let me write the statement. For this guy, we have x minus x2 implies that this is less than 0.1. Is that okay? Yes, that's correct. So what's the lesson here? Nope. Don't crash. The lesson is that for some functions, like 1 over x squared, which we'll talk about later, as x naught varies, the choice of r must also vary to get desired precision epsilon. Okay, so this is when things go bad. When do things go good? Take f of x to be 2x, 4x in R, in fact, and give me any point x naught in R, and precision epsilon positive. So we want to find R positive so that x minus x naught less than R implies that this is within epsilon. So we reverse engineer. We have 2x minus 2x naught less than epsilon. We factor out the 2. So I'll do it step by step. Then we open the absolute value. So we get that. We get x has to be within this. But note that the difference does not depend. So, but note R does not depend on x naught. So let's see what the picture is. So this is 2x. And you give any x naught. And you ask to be within epsilon precision. Then we're saying that this ball will always have the same radius. For all x naught. Okay. All right. So Good. All right. So definition of a uniform continuity. Let S be in Rn and function S mapping to Rn. We say F is uniformly continuous if the following is true. If for precision epsilon 0, there exists a global R positive such that for all x naught in S, we have the following: x minus x naught less than R implies f of x minus f of x naught is less than epsilon. Okay. No, you don't have to show the question is, should we be showing the reverse engineering steps? No, you don't have to. What else? Yeah, we're motivating uniform continuity. Yeah, good. But this definition is very hard to work with. So here's an equivalent one. So proposition. Equivalent criterion for uniform continuity. Okay, so F is uniformly continuous on S in Rn if and only if how do you say this? For any so we'll define this for any equivalent sequences. So we talked about equivalent sequences in Cauchy, but let me go over it again. I.e. The limit of an minus bn 0. We have that the sequences f of an and f of bn are also equivalent. Okay, let's see. Okay. Yeah, I will prove this. Let me prove it. You can read the examples, and I will do an example after. All right. So which direction? Let's do uniform continuity implies equivalent sequences. So that means if AN, BN are equivalent, want to show f of AN, f of BN are also equivalent. All right. Good. All right. So okay, one nice way to do this is with contradiction, as usual. So by way of contradiction, how do you say this? Assume that there exists epsilon naught, so that f of an. So even though an bn goes to 0, yet these guys are lower bounded by epsilon naught. Okay, so let's see. Right. So take it's a little bit tricky. So take so let me do it for convergent sequences, and then I will generalize it. So let AN converge to L1 to L, and so the same is true for BN. Then, indeed, we get a contradiction by a sequential continuity. So that's case one. Okay, now suppose they don't converge, but they're bounded. Suppose this is case one. Suppose that A and Bn are bounded. Meaning, A and Bn are within a closed interval minus Mn. Then repeat argument by extracting convergent subsequence. subsequences. Okay. So, okay, I will finish next time. Yeah, so your tutorial starts 12. I'll stick around here for questions. So we will continue this next time. Okay. So you can go to your tutorial. I will stick around here for questions. You can ask questions here. So I have a separate link for office hour for Friday. Yeah, but here we can just talk here. It's fine.